Okay, so we have a trapezoidal graph here, and everybody seems to have recognized immediately that this graph is an exponential function, that of an exponential function. You've got a height of 1/4, 1/2, 1, 2, and 4, and everybody has a good sense of where those numbers come from. Okay, so we go to the interval 0, 1, and we label this interval. Okay, we can see what the labeling is, but let's see how we got it. This number should be the slope, this number should be the area. Slope on the interval, well, we do the rise, we find that it's 2 minus 1, because that's from here to here. And the run is 1 minus 0 is 1. Slope, rise over run, well, that's 1 divided by 1, it's 1. Midpoint of the graph, the midpoint graph altitude. Now we got off in a little tangent there, but that was a good one because it told us a lot of stuff. So when I asked for the midpoint graph altitude, people said, well, let's see. We located the midpoint through an algorithm, and some robot or something did this. And then we proceeded to reconstruct this into a rectangle, which isn't necessary for finding the midpoint, which is our question, but that's what we're going to use the midpoint for, so it was a perfectly okay thing to do, right? But to find the midpoint, well, the midpoint is here, and the midpoint graph altitude is this distance. Well, you're going from 1 here to 2 here. This is a straight line, and this is halfway in this direction, so it better be halfway in that direction. And halfway from 1 to 2 is 1.5, right? And it's the same thing as what you get if you add 1 and 2 and divide by 2. It's the average of the two numbers, the mean average, okay? So we get that, and I calculated it as 1 plus 2 over 2, which is 3/2. So that when we reconstruct this into the rectangle, we have an altitude of 3/2, graph altitude of 3/2, and a width of 1. So the rectangle has dimensions 3/2 by 1. Its area is 3/2. Okay, 3/2 times 1. Now we do the same for this, and clearly the midpoint altitude would be 3/2. So I'm not going to write that down because it's not part of our labeling, but we kind of do this so we see it. But the midpoint altitude is 3/2, so that the area is what? Width times midpoint altitude. The width is going to be 2, the midpoint altitude is 5/2. 2.5, right? And that gives us an area of 5. So we can put a 5 here. And a slope. It's rise divided by run. The rise from 1 to 4 is 3, 4 minus 1. And the run is from 0 to 2, that's 3/2. Those are the numbers I'm seeing on the papers of people who didn't make little silly arithmetic mistakes. Okay? Make sense? So we understand this. Now we can proceed to label the rest of the trapezoid, the rest of the graph. Although the regions get kind of small and hard to insert numbers into, well, we could do that. But what I really want to focus on is the fact that, okay, we've labeled this one and this one here. Now, what's the total of these two areas?
3. No.
3 3/2.
Yeah, well, when you add 3/2 to 3, what do you get?
4 1/2.
You get, okay, well, you get 9/2, right, which is 4.5. Okay? So this, the area, the region beneath this trapezoid has area 4.5, 4.5. This has area 5. Why does this have more area than this one? It's the same graph.
We must have done something wrong. Oh.
Okay, this trapezoid,
We didn't take into account the curve.
yeah, has area 5. That's a good way to say it. this trapezoid has area 5, the two trapezoids on the same interval have total area 3/2 plus 3 equals 9/2 equals 4.5. Now we do want to write 4.5 because we can immediately compare 4.5 with 5, whereas comparing 9/2 with 5, we either have to say, well, that's 9/2 and 10/2, or more conveniently, we go ahead and express it as a decimal. And if we have to approximate the decimal, we approximate to a reasonable number of significant figures so we can see the difference between one number and another. Okay? There's more to that. We'll see how that goes. Okay? And why is this? Because you said we didn't account for the curvature. There's not really a curvature here, okay? Because we have straight lines. Each line has no curvature, right? But that's the right idea because, of course, the graph itself has a curvature, right? And because of the curvature of the graph, the sum of these two is not equal to this, right? Sum of these two areas is not this area. Also, what about the average of the two slopes? If we average the two slopes, looks like we do get the average slope, right? What if that's a property of exponential functions? Okay? So, okay. This tells us that, okay, our picture looks something like this. We've got the 4, we've got the 1, and we've got the 2, so we've got this, right? That's this picture. And for this picture, the total area appears to be 4.5. Okay? For this picture, just kind of superimpose this. We just cut directly from this point to this point, right? And because of the way the curve is concave upward, okay? The area, if we project, if we just cut from here to here, is greater than the area that we have here, right? So it's pretty clear why those areas are as they are, okay? And we can kind of extend this. I mean, it would require proof, but we at least conjecture. This is a more abbreviated statement than I wanted. I'll call this graph a finer graph than this. We're breaking things down more finely, right? That makes sense? Does that word kind of seem appropriate? Okay? I needed a longer statement here, but I'm going to go with the one I have. When you subdivide your intervals more and more, you get less and less area, right? Okay? So I can kind of make a statement up here.
What's the word in the quotes on the bottom?
What's what now?
F-I-N-N-E-R.
The what?
F-I-N-N-E-R. She
Finer.
wanted to know what it was.
Okay, that's, yeah. That's the word finer. Okay? So up here, I'm going to make a little better statement. Hopefully I've got room to write it out. I don't know what's going to come out of me, but we'll see. Okay, when the intervals are actually, there's a word I want to introduce now. So I'm going to pretend I didn't yet say that. Okay? Okay, I want to talk about partitions because then we have a language where I can express this succinctly. Okay? Okay, so without writing a definition of a partition, there's an example of one. Okay? What do you think the word partition means here? If this is a partition of this interval.
Like a full,
Again?
like a full kind of, like all the numbers within something.
Well, we don't have them all, you know, way too many. But, okay,
All the integers.
well, yeah, but a partition doesn't have to always be integers. Obviously, if we were doing this with some of the other functions, we'd have like 1/2s. Okay, we don't use 1/2 for our basic exponential function. So we're not going to confine ourselves to intervals, to integers, but you got the right idea. It's a way of breaking up the interval, okay? So a partition's a way of breaking up an interval. Now, can be more specific about that. You got to break it up in such a way that none of the sub-intervals overlap, but that they cover the whole interval. So I'm going to say this is a partition of the intervals into the sub-intervals. Now I'm doing something I might regret by making this closed intervals, but okay, these are your sub-intervals, okay? And I'll observe that these intervals, is there an overlap between these sub-intervals? Actually, there is. Okay, where do they overlap? I'm sorry? Okay, yeah. They overlap at all these endpoints here, except this one and this one, right? And these cover the interval -2, 2. Overlapping only at the endpoints. Okay? Does that make sense? So the subintervals have to include everything in the interval. You could say that this interval is the union of all these, right? This one, union with this one, union with this one, union with this one, equals this one. Okay? So I'm actually going to say that because that's really important notation. So I'm going to say that going to say this. Now, we might decide that we would want to use half-open intervals. Okay? So, this would be a parenthesis, this would be a parenthesis, this would be a parenthesis, right? Then we wouldn't even have to worry about the idea if there's overlap. Okay? And that's also a pretty good idea. But I'm going to stick with the closed intervals, although it's not really the way you rigorously define a partition. You can understand the rigorous definition if you understand this one. Okay? The rigorous definition to have half-open intervals for every interval except the last one. The usual definition. It doesn't make any difference for what we're doing right now, and it probably doesn't make any difference for anything you'll ever do. But if you do end up in higher level mathematics beyond your 2 years of calculus and a year of linear algebra, okay? It would make a difference, but at that point you'll understand. Okay, so anyhow, that's a partition. Yes? Yes?
No.
Okay, as soon as you're gone, we're going to talk about stuff you're not going to understand. No, we're not going to do that. You'll understand.
Okay.
Lunch, question mark?
Okay, now,
Lunch question?
how about this? It's important to express things in set theory. Because set theory is really foundational for all of mathematics. When you get to the level of the art of computer programming, you got to know quite a bit of set theory. Okay? So we could say the partition is this. This is a set consisting of all these intervals whose union is the set and which overlap only at endpoints. Okay? Another partition is this. Does that fit the criteria? Do those intervals overlap anywhere except at the endpoints? No, the only place they overlap is at 0, right? And you can get rid of that by using half-open intervals if you don't like that. Okay. And if you put these two together, if you form their union, does it give you the whole interval? Yeah, they overlap at endpoints, the union's the entire interval, so it's a partition. Okay? So, we can also say that this partition is a refinement of this partition. I'll say since every interval of the first is a subinterval of the second. What's that mean? What do I mean by a subinterval?
An interval of an interval.
Okay, well, let's take the interval -2, 0, right? Would you say this is a subinterval of this interval? Yeah. Would you say this is a subinterval of this interval? Would you say this is a subinterval of this interval? Is it a subinterval of this one? Okay, is this one a subinterval of this one? Okay, so what I've done is I've divided both of these intervals into 2. I could have divided them into 12 as long as I still have a partition. As long as my refinement covers the whole interval, overlapping only at endpoints. Okay? Okay, so that's a partition. Now, partitions are extraordinarily important. Like second semester of a calculus course. Okay? You're basically doing this. Even though the way it's presented, it might not look like it. This is what's really going on. And the way things are often presented is give somebody a shortcut to understanding what's really going on. Okay, so anyhow, we see then that, okay, we could have done this with our trapezoids, right?
Yes.
What's our partition here? The partition corresponding to these trapezoids, well, actually, I probably should have left this here, is just this one, isn't it? I've got a trapezoid on the interval -2, 0, and another one in the interval 0, 2, right? Understand, Lauren? Told you wouldn't miss anything. Okay? Okay, so this is the trapezoidal graph that corresponds to the exponential function on this partition. Okay? Now, this trapezoidal graph, which we could complete the labeling of if we wanted to, corresponds to this partition, doesn't it? Make sense? Okay? The first partition is a refinement of the second. Okay? In other words, we've got this partition. If we refine it by cutting these intervals into smaller intervals, well, we could get something. This is a refinement, right? So this is what I mean when I say this is a finer graph, okay? It's a graph on a refined partition. And we understand that we could then subdivide this partition, right? We could refine this partition. We could go -2, -1.9, -1.8, and so forth, right? Of course, we'd have numbers that we don't know how to calculate when we try to evaluate the exponential function, but you know, the calculator spreadsheet would do that for you, okay? Make sense?
Mm-hmm.
But nothing here requires anything that you can't do with very simple 5th grade arithmetic, right? Okay? So we want to base everything on simple arithmetic, simple ideas, so that when we go to the crutch, and everybody needs the crutch to evaluate e to the 1.9. Actually, not everybody, I don't. Anybody that's had a year of calculus would know how, but, it's irrelevant, you're not gonna do that, you're gonna go to the calculator.
Can you come teach my calculus class at my school,
No,
please?
I would love to, but I can't.
He can
Okay.
come take his calculus class.
Huh?
He can come take your calculus
Wait, can I
class.
commute from the school during high school?
I don't teach a first year calculus. Everything I teach is a second year. Will across the hall teaches a first year, he's really good.
Would I be able to commute to his?
You could, if your school schedule permits, but that can be tough. Vincent was talking about a couple of students that want to come down and take Will's calculus class, but working out the schedule where they can do it.
I'm gonna be taking pre-calculus and calculus next year.
Pre-calculus and calculus? Yeah, I don't know that you can, I don't know how that's set up. I know you can do pre-calculus in one semester, okay? And I didn't used to think that was a good idea, but the results people are getting in the schools from pre-calculus look pretty adequate. They look like they're as good as ours, okay? It didn't look that way for a while because students were blowing off the assessment test. So look, and grading patterns needed to tighten up just a little bit. They were being, dual enrollment was being graded a little bit easier, but that's not the case anymore.
Easier.
The grading patterns and the results in assessment were so identical for our class sections and the school sections that it was astounding. I couldn't believe it, okay? I mean, I was happy about it. It was beyond my wildest expectations. And now that we've empowered our dual enrollment people, I would not be surprised if they start exceeding us. Okay, they do a great job. In pre-calculus, we haven't assessed. We've got an assessment from the applied calculus now. I haven't had a chance yet to look at those because I just got them the other day. Okay, well, anyhow, that's beside the point. The pre-calculus at least is going to be great. You would not do any better by taking it here. Unless you took my course, which would be crazy. Nobody wants to do that. Okay, I do it a little bit differently, but my assessment results are pretty much the same as everybody else's. You work with what you've got. The difference between the high schools and here is that here, half of our class drops a course
So you're about the only one in.
because we have a ridiculous placement policy in Virginia. My opinion, they're really good people, really smart people whom I totally respect, who have a different opinion. And, you know. So I respectfully disagree with their opinion, and they think I'm a complete idiot. I don't know. I think they respect. We'll see how it works out. We're going to get some statistics on it. It's new. Okay, well, that's a digression, but we understand partitions and refinements. So what I'm saying now is, on an exponential function, if we refine the partition, our estimate goes down, doesn't it? Why? Because the curve is concave up, and every time we refine a partition, our middle point is lower than the straight line would have been. So let's make sure we understand that. Okay? So, for any function that's concave up, and that would include the x squared function, right? Okay? So, now this is no longer an exponential function. It might not be an x squared function either. But okay, here's a partition, right? Whatever these numbers are and whatever this thing is, that represents a partition. Okay? Getting a little bit long, but that's okay. So this is concave up. And here's a partition. Partition's implicit. It's this number, you know, this interval, okay? Whatever this is. I'm not going to put letters on it because that would only confuse the picture, okay? Okay, so, now we're gonna do a refined partition. If I can find color of chalk, you wanted green before. Okay? So refined partition, well, I'm gonna draw a line that's not directly over this one. So we can still see the original partition, but these lines are supposed to be right on top of each other, right? So we see green and white here, we see green and white here. I got the green a little too close to the white here. So let me make sure we can see both colors. So these two lines are really right on top of each other, but if I draw them that way, you can't see them. Okay? So we refine the partition. Now I'm just going to refine it by cutting it into two parts. Normally you would probably cut it in half, but it's not necessary. You could refine it with any numbers in between. Okay, and sometimes there's an advantage to doing that. So don't feel like you're constrained to that. Okay, so on the original partition, right here are the trapezoids, right? So on the original partition are trapezoids. Might look like this. On the refined partition, first of all, we have the exact same lines that we have up here, right? Exact same graph altitudes, but now we've got graph altitudes in between. Okay?